All right, let's take a look at confidence intervals. So a fairly typical situation is we take a sample of our population and we find some information about it. So here we have a sample of size 100, we find the mean weight, and we find the standard deviation. And what we want to find out is what can we say about the population mean based on this information that we've gotten. Now the sample is large enough so that the central limit theorem applies, and that tells us that the sample mean will have a distribution that is approximately normal, where the mean of the sample means is equal to the mean of our population, and our standard deviation is going to be related to the standard deviation of the population in a very predictable fashion. Now, this actually requires knowing what the standard deviation of the population is, and we don't have that, so we generally approximate our standard deviation of the population with our sample standard deviation. And this will give us our standard deviation of the population of the sample mean. So substituting those values in gives us a standard deviation of the sample mean, 0.04. What about our mean? What about the mean of the sample mean? To see where we get this, we go back to the central idea behind hypothesis testing. The key question is, we want to find the population means that are supported by the observation. Equivalently, we want to find the population means that we cannot reject on the basis of what we have observed. So let's think about this as a hypothesis test. We would make a hypothesis, for example, the mean is 16.0 ounces. That's completely arbitrary, but it's going to serve as a good example. And my central limit theorem says that if I pull a sample from a population with a mean of 16.0 ounces, then the sample mean would be normally distributed with a mean of 16.0 ounces, and our standard deviation, which would be what we calculated before, that standard deviation of the sample mean, 0.04. And now that I have the mean and the standard deviation, I can apply the 1, 2, 3 rule. And that tells me that 95% of the time I'd see a sample mean within 2 standard deviations of the population mean. That's going to be, roughly speaking, from about 15.92 ounces up to 16.08 ounces. And so I have a rule now at the 5% level of significance. I should reject the null hypothesis if I observe a sample mean of less than 15.92 ounces, or if I observe one more than 16.08 ounces. And now we go back to our observation. What we actually saw was a sample mean of 15.9 ounces, and so on the basis of this rule at the 5% level of significance, we would reject the null hypothesis that the mean was 16.0 ounces. But I can also consider other null hypotheses. For example, let's take the null hypothesis the mean is 15.95 ounces. Let's go ahead and set up a test that will reject or fail to reject this null hypothesis at the same level of significance. And that's still going to be our plus or minus 2 standard deviations of the mean. So with the 5% level of significance, I'd see a sample mean between 15.87 and 16.03 ounces about 95% of the time, and so my 5% level of significance rule gives me reject the null hypothesis if you observe a sample mean of less than 18.57 ounces, or if you see something more than 16.03 ounces. And again, we have our observed sample 15.9, and this is actually inside this interval, so that tells us we would fail to reject the null hypothesis. And so this 15.95 ounces is something that we could not reject based on our observations. So now what we're going to do is we're going to put together all of these null hypotheses that we cannot reject at our given level of significance. And all of those null hypotheses put together will be our confidence interval. So what does that confidence interval look like? Well, we know that our observation caused us to reject the null hypothesis the mean weight was 16 ounces, so 16.0 ounces is going to be outside of our confidence interval. At the same time, our observation caused us to fail to reject the null hypothesis 15.95 ounces, so 15.95 is going to be inside the confidence interval. So now we want to find the greatest and least values that will fail to be rejected as null hypotheses by our observation. To determine these, suppose my null hypothesis is that the population mean is equal to some numerical value. Now, the central limit theorem guarantees that the sample of size n will have a probability distribution that's approximately normal, where the mean of the sample mean is going to be m, and the standard deviation of the sample mean will be given by our formula. So again, keeping to our 5% level of significance, we've come up with a rule that says we're going to reject the null hypothesis anytime we observe something that's less than 2 standard deviations below the mean or more than 2 standard deviations above the mean. So this means if our sample is within 2 standard deviations of the mean, it would fall inside this interval, and we could not reject the null hypothesis. That means that the population means we'd fail to reject are all of those that are within 2 standard deviations of our sample mean. For example, our sample mean was 15.9 ounces, and we computed the standard deviation of the sample mean at 0.04 ounces. At a 5% level of significance, we got a 95% confidence interval that was mean plus or minus 2 standard deviations, and that gave us a range from 15.82 ounces up to 15.98 ounces. And so we can say that for our sample size n equals 100, the sample mean 15.9 ounces gives us a 95% confidence interval in the range 15.82 to 15.98 ounces. Now, what's important is not to misunderstand what this means. So let's take a look at, first of all, what it absolutely does not mean. So here's our statement about what our confidence interval is. Once again, we have our 95% confidence interval, and what it doesn't mean is anything about the probability that the mean is in the observed interval. So even though we have a 95% confidence interval of this amount, that does not tell us that there is a 95% probability the mean is going to be located in that interval. This is false, and it is very, very false. So what does it actually mean? Well, what it actually means is that take any value that you want inside this interval and make that your null hypothesis. Then run a hypothesis at the complementary probability, the 5% level of significance, with null hypothesis population mean equals that value that you chose inside this interval. If you were to run that hypothesis test, you could not reject the null hypothesis on the basis of your observed sample mean. At the same time, for anything outside this interval, for example, 16 ounces, 15.75 ounces, or anything else, for any value outside that interval, if you were to run a hypothesis test at the corresponding level of significance, you would be able to reject that hypothesis and embrace the alternate hypothesis. That's what the 95% confidence interval tells you. It is the null hypotheses that are not rejected by the observed data.